everything in the universe has a beginning. But how can the universe itself have a beginning? Does the universe come with a start date? Does a cosmic commencement make sense? I am haunted by this question. Creation is humanity's ancient and perpetual fascination, and cosmology is the scientific study of the origins and outcomes of the universe. Recently, cosmologists have been making radical, revolutionary discoveries.
The universe was extremely dense.
Did our universe have a beginning? I'm Robert Lawrence Kuhn, and this is my journey to find out. I like to start with the big picture, so I start with Martin Rees, the UK Astronomer Royal, who has the rare gift of being both visionary and level-headed. We meet in his home at Cambridge University. Martin, in struggling with the great questions of existence, what it's all about, I can't think of a more powerful probe to reality than the simple question, did the universe have a beginning?
Well, of course, we're fascinated by origins in all contexts. We had an origin. We believe life has an origin on the Earth, and we're coming to understand that perhaps even the universe did, although we're not quite sure. Although, for a long time, people have been aware that there is change and decay here on the Earth, it wasn't really till the 20th century that we understood that stars themselves have a life cycle. They form, they evolve, and they die. They have a limited energy store from nuclear fusion, and so there is a sort of life cycle of stars. But even that didn't require that the universe itself had a life cycle. Indeed, there was a theory, particularly popular in the UK in the 1950s and 60s, that the universe was in a so-called steady state. The idea of this theory was that the universe was expanding, but that as the galaxies moved apart, new ones, as it were, formed in the gaps, so that the universe itself existed from everlasting to everlasting in a steady state. That theory has been shot down by our realization that the universe was not the same in the past. We can look far back in time by looking at great distances, and we see that things weren't the same then. The first such evidence came in the 60s, and now the steady state theory in its simple form, no one accepts. People accept that the entire universe is evolving, or at least developing.
What are some of the primary evidences that made that distinction so clear?
Yes, well, the first bit of evidence was that very distant galaxies looked different from present-day ones. That was the first evidence for a non-steady state. But much the most compelling evidence came in 1965 with the discovery of the so-called background radiation, the evidence that even intergalactic space is warmed to 3 degrees above absolute zero by microwaves, which are an afterglow of the hot Big Bang. And I would say we can, with great confidence, go back to the stage when the universe was a millisecond old, maybe even a billionth of a second old. And the reason we can do that is that all through the time span after the first billionth of a second, the physics which prevailed in the universe was physics which we can test here on Earth in the lab. And also we have fossils in the universe now of those early phases. For instance, the proportion of helium and hydrogen in the universe is determined by what conditions were like in the first few seconds of cosmic history. If the Big Bang Theory is correct, then many key features of our present universe, its uniformity, its content, the mix of matter, radiation and dark matter, were all determined by a process in that first tiny, tiny fraction of a second.
I need to understand data, facts from observations. So I seek out Wendy Freedman, a principal investigator on the Hubble Space Telescope's project to measure the rate of the universe's expansion. Wendy is director of the Carnegie Observatories in Pasadena, California. As I, like almost everyone, have struggled with the ultimate questions of existence, the expansion of the universe has come to characterize the reality of these questions. I come to you as one of the world's experts on understanding the expansion to help me understand it as it really is.
What we've been able to measure is that the universe is expanding. We see that galaxies that are more distant are moving away from us faster and faster. This was a relationship discovered by Edwin Hubble in 1929 in the context of Albert Einstein's general theory of relativity. What this allows us to do is to essentially run like a movie running backwards and say, okay, how long then has that expansion been occurring over? And so if you extrapolate back, you get to a time when the universe would have been much denser, much hotter, and a time we refer to as a Big Bang origin for the universe. For example, if there had been a Big Bang, an explosion sometime early in the universe, you ought to see the remnants of the radiation from that Big Bang. And we do see that. You can predict, in fact, that it would be cooler now because the universe has been expanding in the intervening time, and we see the uniform background radiation. Now it's 3 degrees above absolute zero, very cold temperature, but we see it everywhere over the sky, which is evidence for an earlier fiery beginning to the universe.
You have two totally separate pieces of data?
In fact, there are more. You would predict that when the temperature was really hot in the early universe, you would form the elements, light elements like hydrogen and helium, and you can predict very accurately what the relative abundances of those elements would be. When we go out and measure those abundances, they fit precisely with what you would expect if there had been an early beginning in a Big Bang.
And how about looking at the individual components within the universe, age of galaxies, stars, rocks on Earth? How do they correlate?
They're consistent. So when we measure the ages of the rocks on Earth, they're 3-4 billion years old. If we measure the ages of stars in our Milky Way galaxy, they have a range of ages up to about 12 or 13 billion years. So we have independent clocks that can give us estimates of the age of the objects that we see in the universe, and they are consistent with the same timescale that we measure by measuring the expansion.
And what is its age?
It's about 13.7 billion years.
And that is absolutely remarkable that we human beings on this earth with a sentient life of a few thousand years and a scientific history of a few hundred years can measure so accurately the beginning of the universe 13.7 billion years ago.
It is a remarkable achievement. I think the discovery of the expansion of the universe is probably one of the most profound human discoveries of all time.
So, Wendy, it's that simple? Just run the movie of the universe's expansion in reverse? Does that prove that the universe did, in fact, have a beginning? Here's what impresses me. Multiple tests and independent measurements, all of which converge on a similar age of the universe. Okay, data suggests that the universe had a beginning. But what could that possibly mean? I need to dig deeper. So I visit Alan Guth at MIT. It's no exaggeration to say that Alan changed humanity's concept of how the universe began. Alan, one of the great perennial questions of human beings throughout all history, and it applies to us today, is to look around at our universe, see it in a remarkable way that we understand today more than ever before, and ask, did it have a beginning? How do we think about that question?
Well, in the first instance, we look at what the universe is doing today and try to extrapolate backwards. When we do that, we see the universe is expanding today. When we extrapolate that backwards, it gets smaller and smaller, and ultimately, presumably, came from something extremely small and dense. Now, that still leaves the question of whether or not this hot, dense state was really the beginning, or whether or not there may have been some prehistory to that. The theory that I've worked on, called inflation, seems to imply that there almost certainly was a prehistory, but still there would be a beginning someplace. Inflation is basically an attempt to explain the bang of the Big Bang, what set the universe into this period of gigantic expansion. It turns out the conventional Big Bang theory really said nothing about the Big Bang itself, the propulsion mechanism. Inflation takes advantage of ideas coming out of particle physics, which tell us that at very high energy densities, there's a prediction that there should exist forms of matter which literally turn gravity on its head, causing gravity to become repulsive. So this repulsive gravity would be the driving force behind the Big Bang. The assumption would be that the early universe contained at least a small amount of this repulsive gravity material. It drove then an exponential expansion, which became the Big Bang of our universe, the driving force behind the expansion.
What is it about inflation that makes the possibility of prior universes or subsequent universes conceivable?
It has to do with the way inflation ends. Inflation ends, we believe, because this repulsive gravity material is fundamentally unstable. So, like a radioactive material, we believe that this repulsive gravity material had a half-life. The decay was exponential. A certain amount of time, half of it decays, wait, same amount of time again, half of what remains decays. But the catch here is that while it is decaying, it is continuing to exponentially expand. So it works out that if you wait one half-life of the decay, half of it has disappeared, but nonetheless the half that remains is nonetheless larger, and in fact vastly larger than the region that you started with. So even while it's decaying, this repulsive gravity material increases in volume and will then therefore, according to these theories, never disappear, but go on inflating forever with pieces of the material decaying and producing universes, which I usually refer to as pocket universes. But one of these pocket universes would be in fact vastly larger than our observed universe, and our observed universe would just be a tiny piece of one pocket.
Wow.
Right. This process seems to predict that the universe will go on with pieces of inflating forever, eternally into the future, and we refer to it as eternal inflation. But the word eternal is being used slightly loosely. Semi-eternal might be more accurate. It's eternal into the future. We do not think that it's eternal into the past. Making assumptions that seem reasonable, we've been able to, quote, prove mathematically that it's in fact not possible to extrapolate arbitrarily far into the past.
So time's arrow in Alan's universe is not symmetrical. While cosmic inflation may engender innumerable universes forever into the future, it cannot do so into the past. Even inflation demands that the universe had a beginning. I'm ready for more data. I focus on the cosmic background radiation, that afterglow of the heat of the Big Bang, which fills the sky in all directions and which showed the steady-state universe to be false. George Smoot won the Nobel Prize for his measurements of the cosmic background radiation. He took pictures of the early universe, which changed how we understand our origins. I visit him in Berkeley. George, the remarkable picture of the cosmic microwave background has been called the photograph of creation, the face of God, all sorts of extraordinary language. I want to know the real science behind it.
Okay, well, I think of it as a photo of the embryo universe, sort of like when you're growing up, there were baby pictures and so forth. This is a picture of the universe was an embryo, sort of like the ultrasound, and that's an analogy that's very good in many ways. So let me explain why it is, because it's a photograph of what the universe was like about 400,000 years after the very beginning, which seems like a long time, but remember the universe is nearly 14 billion years old now. And so putting it in human terms, if the universe is in middle age now, that's 12 hours after conception. So that's when the ultrasound is. Okay, so why do I call it an ultrasound? Well, what you see first when you see it is like looking at a picture of the sun, you see the sun. Later on, if you look more carefully, sometimes you see sunspots, some irregularities on it. But if you look more carefully, you see there's all kinds of standing acoustic waves in the sun. There's just sound waves going all around the sun. And looking at them tells us about the properties of the sun. The same thing is true of the early universe. When it was made, it wasn't made quite perfectly. There were small irregularities in it, and those irregularities show up as sound waves. And when you do the ultrasound, you see the sound waves, and they show up, and they see things that later on are going to manifest themselves the same way the tiny structures you see on a 12-hour-old embryo will turn into a human being. We see the structures that are going to turn into the modern universe.
Yeah, we like those imperfections. If they weren't there, we'd be in trouble, right?
They're what make the universe interesting and also make it possible for us to be here. We wouldn't have stars, we wouldn't have galaxies.
If everything was exactly the same.
We wouldn't have planets, we wouldn't have us. Those are really nice features. They're extra features added to a very simple, very uniform early expansion of the universe. And so there's this incredible, you start with this very simple thing, and over time, complicated structure forms and it evolves and gets more complicated until you see something as rich and complex as the world. So it's really cool. It's way cool. I mean, when most people, don't understand this part, but I mean, you're taking things that are smaller than a proton and you're making them the size of clusters of galaxies.
Unbelievable.
And it's just so spectacular.
An ultrasound picture of the embryo universe. Galaxies and clusters of galaxies germinating from a seed smaller than a proton. All this, the product of the very early, very hot, very dense, very tiny universe. But where did all this early stuff, no matter how small, come from? Theology may posit an answer, but science, it would seem, cannot. But physicist Alexander Vilenkin claims to have an answer. Trained in Russia, he is now at Tufts University in Boston.
Alex, one of the great questions of humanity from time immemorial has been the question of origins. So I want to come to you as a cosmologist who has been very intimately involved in the beginning of the universe and ask that question. Did the universe have a beginning?
One thing that we know for sure is that we live in the aftermath of a great explosion that we call the Big Bang. The universe, about 14 billion years ago, the universe was extremely dense and hot and rapidly expanding. Now, was that the true beginning of the universe? Actually, cosmologists now believe that it was not, that there was a stage prior to the Big Bang, which is called inflation. It ended basically with the Big Bang. Still, the question remains, what happened before inflation, if anything? And it appears that a satisfactory answer can never be given, because I can keep asking, and what happened before? There is one scenario that breaks out of this infinite regress, and that is somewhat popular now among the cosmologists. And this is the scenario that the universe could originate spontaneously out of nothing. This sounds like a very strange proposition for a physicist to make, because we know that there are conservation laws, that energy is conserved, right? So usually this means that if you have nothing, you cannot have something, because that takes energy. However, it turns out that if you have a closed universe, where the space closes on itself, like in 2 dimensions, the surface of the Earth closes on itself. And 3-dimensional space can close on itself in a similar way, so that you go in some direction and you come back to the same point after you traverse the whole universe. So in such a closed universe, the gravitational energy, which is always negative, exactly compensates the positive energy of matter. So the energy of a closed universe is always 0. And then nothing prevents this universe from being spontaneously created.
Because the net energy is always 0.
That's right.
The positive matter balanced by the negative energy of the gravitation of that matter, which is the space-time curvature.
That's right. So there is no conservation law that prevents the formation of such a universe. And in quantum mechanics, actually, if something is not forbidden by conservation laws, it necessarily happens with some non-zero probability. So a closed universe can spontaneously appear out of nothing. And there is, in fact, an elegant mathematical description of this process, where a tiny closed universe having very high energy spontaneously pops out and immediately starts to expand.
Okay, but when we say that this quantum mechanical fluctuation appears out of nothing and we have the balance of energy, and so we're in conformity with the conservation of energy laws, yet you need the laws of quantum mechanics. You need some pre-existing environment that can enable this to happen.
That's true. This is a very perplexing mystery that in this picture, the same laws that describe the evolution of the universe also describe the appearance of the universe, its coming into being. And this seems to suggest that the laws were there prior to the universe itself.
The universe originating spontaneously? Out of nothing? This is not absurd, because the laws of quantum physics require particles to be popping in and out of existence. But Alex still has those pesky laws of physics to deal with. I'd like closure of sorts, at least for now, a coherent picture or story I can embrace. So I turn again to Martin Rees.
And it's only because we can imagine time measured by clocks ticking away that we can talk about before and after. And some people say that the idea of what happened before the Big Bang is something which is an improper question, like asking what happens if you go north from the North Pole. You just can't do that. Others think that there may be a more complicated relation between space and time. There may be other Big Bangs. I would say that the chain of events, which started maybe a billionth of a second after the very beginning, is a chain of events which we understand in outline and which we should take very seriously indeed.
So it seems our universe did have a beginning. We call it the Big Bang, but the Big Bang was not the beginning. It emerged from the cauldron of cosmic inflation, when something infinitesimally small expanded majestically in an astonishingly brief instant, cooking up space, time, energy, and matter in a colossal cosmic stew. Three little questions: when, how, why? When? 13.7 billion years ago. We've nailed the date with remarkable precision. How? What caused it all? Perhaps quantum fluctuations, perhaps some prior state. But however it happened, the laws of physics made it happen. So we come quickly to why. Why did our universe begin? Why the laws of physics? Sometimes only silence gets us closer to truth.
For complete interviews and for further information, please visit closertotruth.com.